So, as we saw in class last time, to solve most linear differential equations that we're going to encounter, it's important to do a partial fraction expansion on your Laplace transformed function y of s. So to do this, there are several cases we have to consider. The first is when the poles of your transform are all distinct and real, or individual real poles. Poles are the values of s that make the denominator of y of s equal to 0. And as we'll find out, most often the denominator is simply a polynomial, so the poles are easy to find if you can factor the polynomial. So when you have individual real poles, the partial fraction is of the form y of s equal to some numerator as a function of s divided by some denominator as a function of s. And if you can factor the polynomial, which you should be able to do with individual real poles, then we have n of s divided by s plus a1 times s plus a2 times s plus a3 dot 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 s plus a sub n. And then the partial fraction expansion ends up being some coefficient c1 over s plus a1 plus some coefficient c2 over s plus a2 plus dot 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 some coefficient c n minus 1 over s plus a n minus 1 plus some coefficient cn over s plus an. So to fully solve for y of t, you have to find the coefficients. The simplest way to do that is something called the Heaviside Method. So to find these coefficients, we're going to multiply both sides by s plus ai, and then evaluate it at s equals minus ai. So for example, for I equals 1, we end up with n of s divided by, now because we've multiplied through by s plus ai, on the denominator you don't have that term anymore, it's just s plus a2 all the way up to s plus an. On the other side of the equation, because you've multiplied by the denominator underneath c1, you just have c1 by itself plus c2 times s plus a1 over s plus a2 plus dot 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 cn s plus a1 over s plus an. Now this equation should work for every value of s, so let's pick a convenient one. So let's let s equal to minus a1. What that does is that all of these terms become 0. And on the other side, we're just going to leave it at n of s over s plus a2 all the way up to s plus an, evaluated at s equals minus a1, and that is equal to your coefficient c1, because that's the only coefficient left after evaluating at minus a1. Or, more generally, any coefficient that you want to find of this partial fraction expansion, ci, is equal to your numerator divided by your denominator, which has the term s plus ai taken out of it, divided by, or evaluated at the point s equals minus ai.